This is the first screencast for Chapter 20, Electrochemistry, and we'll try to knock this out in about 2 shots. And this is the last chapter that we have of new material for the year. So very quickly, this chapter again is electrochemistry, and it's really more of an in-depth look of how reactions take place. So normally we just look at combinations or decompositions, but to get a better idea of what's going on, it's a lot easier to look, or it's more in-depth to take a look at how electrons are changing place from one substance to another. So in this little example here, we can kind of look, and we did this a little bit before as regards to what's being oxidized and what's being reduced. And we can see that, for example, zinc is losing 2 electrons, and as a whole, hydrogen is gaining 2 electrons based on having 2 hydrogens and getting to hydrogen gas. Okay. So one of the things we mentioned before is if something is being oxidized, that means it's losing electrons, Le. So losing electrons is oxidation. So, okay, we're good with that. And the other side of it is something is gaining electrons. We say that it's being reduced. And I think we're pretty comfortable with that. So gain electrons is being reduced, losing electrons is oxidation. And the other part of this is if something is being reduced, it's oxidizing something else. So if something is being reduced, it is called an oxidizing agent. And if something is being oxidized, it's doing the opposite to the other thing. So it's a reducing agent. So the numbers, how we assign the numbers on these. If you have an elements like iron or oxygen or chlorine, whatever you like, its oxidation number is only going to be 0. But if it's an ion, whatever charge you have, that's the oxidation number or whatever it is. So zinc 2+, oxidation number 2+. Pretty easy. If it's a nonmetal, they typically are going to have a negative oxidation number. So things in the oxygen family are -2, things in the fluorine family, the halogens, are typically -1, but not always, and we'll see how that plays out here in a little bit. And for example, here with hydrogen, if you have hydrogen that's bonded to calcium hydride, hydrogen in this case is a -1 because calcium's a +2. But if you have hydrogen that's bonded to oxygen, oxygen is a 2-, so in this case, hydrogen is a +1. So it just depends what it's being bonded with for hydrogen. Fluorine, always -1. But the other halogens, for example, chlorine, it just depends upon what it's bonded with. So as an example, here we have chlorates, oxygen's 2-, so to get the 1- out of this, chlorine must be a +5, which is really kind of weird, but that's what it works out to get that number, because you get -6 out of oxygen. Okay. All the numbers added up, if it's neutral, have to add up to 0, so the pluses and minuses cancel. And the sum of some of these numbers for a polyatomic will equal out to the charge. So as an example, having sulfates, putting these all together, sulfur in this case is a +6 to give us the total of -2. Okay. So balancing these, the easiest way to go through it is to look at the whole equation and do half reactions. And that's a little difficult to go through in this little lecture, but we'll see it quite a few times in class. And I'll just skip on to the next one. So once you're doing the half reaction method, when you're going through there, you're just assigning these numbers to both sides, and then there's a process to kind of balance it out, which involves right here. The first thing you look at is, all right, if I have oxygen that's not balanced, I need to balance that. And once I balance that by adding water, I balance the other side by adding hydrogens. And then the last thing you do is take a look at the charge and balance out the electrons on both sides. And this is all laid out here in this flow chart you see to the left. And then just like any other balancing, you have to take a look at the coefficients on these and make sure they're balanced out in accordance to the number of electrons. So the number of electrons gained on one side has to equal the electrons lost on the other. And again, we'll see this in class in a much more detail. So voltaic cells is what you normally are going to see in examples. So there's another type of cell which is called an electrolytic. That's easy for me to say. Where you're actually driving it with a charge, with an electrical source. But in a typical voltaic cell, it's spontaneous. It naturally happens. And this is a classic example here with zinc and copper, which we'll see a couple examples in class. So this thing here is called a voltmeter, which measures the potential of that particular cell. And notice the little thing here is called a salt bridge in between. And we'll see a couple different examples of how that can work here in just a few moments. Like now. This little example here, we'll see a couple of these either in class and also on FRQ questions. So this setup will kind of create this in class. But some of the things just to notice here, just to make note of, is oxidation, by definition, takes place at the anode, and reduction takes place at the cathode. And how I once upon a time remembered this is based upon the first letter. These are both consonants, and these are both vowels. You know, whatever works for you. That worked for me. So, again, oxidation, which means you're losing electrons at the anode. And if you take a look at our drawing over here, look at zinc. You see how electrons are flowing away? It's losing electrons, and they're being gained by copper, which is the cathode. So what's happening over here? If the electrons are building up on the side, that means they're being absorbed by these copper ions, and it's turning into copper metal. And then just the opposite's happening over here on the zinc electrode. You have electrons which are leaving the plate, and what's left over coming off the plate are zinc ions. So it balances out in that way. And we've kind of talked about this in detail, so we'll keep moving along. One thing just to mention in addition to this is in order for this to happen, you have to have what's called a salt bridge, which allows a balance of charge. So for example, you'll have these nitrate negative ions flowing onto this side to balance out the positive zinc ions which are coming off. And then also you'll have these positive sodium ions flowing over here to replace the positive charge which is being lost by the copper ions plating out. So you have to have a balance in charge in order for this to work. That's what the salt bridge is for. How do we measure the potential? Again, it's using a voltmeter. That measures the standard potential between these two things. Now let's keep on going. So one of the ways to make these measurements is using, of course, the voltmeter, but just the analogy is the idea of differences in potential energy. So as a waterfall goes from high potential to low potential, so does an electrolytic cell. And they measure that by the EMF, the electromotive force. So again, electrons flow from the anode because they're lost at the anode, and they flow towards the cathode. And that kind of makes sense because the cathode is positive and the electrons flow towards it. And this is measured in the total cell potential, so the EMF of the cell. And just to kind of measure, this is measured in volts, and to break that down, which you don't need to worry about too much, a volt is equal to a joule per coulomb. And we'll look at that more when we talk about Faraday's law, or Faraday's constant, excuse me. So how we measure the potential of a cell, we have to have some type of a reference. And our reference for measuring the potential for reduction, the gaining of electrons, is using hydrogen. So hydrogen by definition is just zero, and every other value you see for reduction potential is in comparison to hydrogen. So we have a little setup here we'll see on the next slide. That we take a look at how everything compares. So I'm actually going to take a break here, and we'll start off with next lecture on this slide here.